In today's lesson, we're going to be connecting back to some of our previous knowledge about statistics. So before we get started, let's take a deep breath. And let's go ahead and begin. So I think that now is a good time to remind you that statistics and probability are not the same thing. Lots of times they get lumped together in mathematics, but they're not the same. Statistics is the study of the representation and the summarization of data. So if you've got a whole bunch of data, statistics is about sort of like finding a more succinct way to express that data. So in this lesson, we're going to learn about how to summarize the data that we get from random variables using statistics. Specifically, we're going to be looking at these 5 things. Expectation, which it turns out is very similar to the concept of a mean, the median, the mode, and then variance and standard deviation. And if you remember from before, these top 3 things are called measures of center, and these 2 things are measures of spread. So that's kind of a quick overview of what we're going to be getting into in the lesson, and so we're going to go ahead and move into the first part of that. The first of these statistics that we're going to talk about is called the expectation of a random variable. And the notation for that is a capital E for expectation, and then the random variable that we're talking about, which you remember from the previous lesson, is generally represented by a capital letter rather. So the expectation basically represents the average or the mean result if we were to carry out that random variable infinitely many times and then average all of them together. And so the next thing I have here is effectively the definition of how we find the expectation. So the expectation of a random variable can be found by multiplying each value of the random variable by its probability and then adding all of them together. So this formula right here may look daunting, but it's really not that complicated. What it says is that the expectation can be found by summing up, and what do we sum up? We sum up each of the different values that the random variable can take, multiplied by the probability that that value happens. So we're going to look at a couple of examples here so that you can see that this is a fairly straightforward thing to carry out. But this is how we're going to find the expectation or sort of the average result of a random variable. I might throw in here really briefly before I move on, actually, that calculating expectation always reminds me of like thinking about grade calculations in classes. Let's say that you know for some class that exams are worth 70% of the grade and homework is worth 20% of the grade and classwork is 10% of the grade. And then let's say that in your case, you've got an 80 on your exams and you've got 100 in homework and you've got a 90 in classwork. If you wanted to find what your score was in the class, you would take your score on the exams, 80, and then multiply by the weighting for that thing, right? So 70% of the class is that. And then plus you take your score on the homework, 100, times the weighting for that. And then plus your score on the classwork times the weighting for that. And you'd add all of these things up, right? I mean, this will give us 56, this will give us 20, this will give us 9. So this is 29, so what is that, 85, I guess? And so that means that sort of like your weighted average for the class is an 85. This isn't exactly the same thing, but you can see that this thing has that sort of feeling of, like you've got the scores here. Those are like the random variable pieces. And then you're multiplying it by, a probability or a weighting. And then you're adding the things together. It's always something that's just sort of, I've been reminded of that anytime we talk about expectations. So I thought that I would share that here. So let's take a look at a quick and easy example. Consider a biased 6-sided die. Bias just means that it's not fair. A biased 6-sided die with a probability distribution shown below. So again, see that I'm showing you a probability distribution through a table like we saw in the previous lesson. And here I want you to calculate the value of E of, that shouldn't have been E of X. This should have been E of S. Because the random variable here is S. We can see that here from the table. If you think you've got a good handle on how to do this from the previous slide, go ahead and try this now. If not, we can go through it together. So to find E of S, what we need to do is we need to multiply each of the different values, those are the top, with the probability of that thing happening, which is the bottom. So to compute E of S, we'll do the first value 1 times the probability of that happening, then the next value times the probability of that happening, and we just go on and carry this out for all of the values of the random variable. 6 times a half. And then it's just a matter of simplifying these things. This is 1 out of 32. This is 2 out of 32. I'm not going to simplify these because at the end I'm going to want to add them together, so I might as well have them, be similar. In fact, in this one right here, I'm going to convert it to 30 seconds as we go down. So instead of writing that as 3/16, I'll write it as 6 30-seconds. Similarly here, this is going to be 16 30-seconds. This next one, I would need to multiply by 8 for the denominator, so this will be 40 30-seconds. And this last one, I need to multiply by 16, so this would be 96 30-seconds. So now, because I wrote all of them with that denominator of 32, I can just add all these numerators together. So I'm seeing this as 161 over 32. It might be worth thinking for a moment about whether this answer makes sense, because remember, this is supposed to be about if I were to do this trial over and over and over and over and over again and average the results that I get, this should be what that is. Well, 32 goes into 161, I mean, like somewhere near 5 times. Does it make sense that 5 would be the average here? And I would say yes, and the reason is, like, look at these probabilities, right? This thing comes up 6 half the time. It comes up 5 a quarter of the time. It comes up less than 5 the other quarter of a time. Like, this die is definitely biased toward the high end. So it makes sense that on average you would get high scores for this. If you did this problem and got an average of 7, that would be bad because the die doesn't go up to 7. If you did this and got an average of 2, that would probably be really bad because this thing has a very, very, very low chance of coming up with a low number. So it's worth trying to think about the answer you get and making sure that it makes sense in the context of the problem. Now, we've got a lot of topics to get through in this video, so I was only able to do one example of that. I'm going to move on now to the median of a random variable. I'm hoping that you remember from statistics that the median of a data set is basically the middle number. You sort of like line the things up in order, and then you find the middle number, and if there's 2 of them there, then you find the mean of those things. We're going to end up having a similar definition for the median of a random variable, but it's complicated to write down, so the example here is going to be really important. So our key point says that the median of a random variable x is the smallest value of that random variable such that the probability of being less than or equal to the median is greater than a half. So it's sort of the smallest value of the random variable so that you push over a half, and that's kind of that middle number idea. If there's a value of the random variable such that the probability of being less than or equal to that is actually equal to a half, then the median is the average of that thing and the next largest value. And that may sound really complicated, but it's really just about finding the value of the random variable where the cumulative probability hits a half. Okay, and so I might sort of write a really, really quick, simple example here so that we can take a look at it and then go on and sort of do the real example that we have in our notes there. So let's say that we had a random variable. Let's call it x. Okay, and let's say that the values on this thing could have been 1, 2, 3, or 4, and the probabilities for these things are 0.1, 0.3, 0.3, and let's see here, what do I have left here then? I guess this would be another 0.3. It's not very exciting, but it is what it is. Okay? So the idea here in finding the median is that what you're doing is you're finding these cumulative probabilities. Okay? So you're saying, it's almost like you're building another part of your table that's, well, what's the probability that I'm less than or equal to this thing? So the probability of being less than or equal to 1 is 0.1. The probability of being less than or equal to 2 would be 0.4, because it's sort of both of these things put together. The probability of being less than or equal to 3 would be 0.7, and the probability of being less than or equal to 4 would be 1. And what our definition says up here is it says that the median is the smallest value of x such that you go above 0.5. And so that's right here. Right here, I go above 0.5, so the median of x is 3. And the reason that sort of makes sense is if you're imagining here in this probability distribution, where do I see the 50% mark? the 50% mark happens right here in the 3 region. Like 10% of it happened at 1, another 30% of it happened at 2. The 50% mark happens somewhere in the 3 range, and so we call that the median. Okay, so now that we've seen this, I'm hoping that the next example that I have is going to be pretty straightforward for you. So I want us to consider here the same probability distribution that we did for the mean, like prior to the median example. And eventually I want you to find the median of S, but the intermediate step is I want us to calculate all of these cumulative probabilities. So this is similar to what we did in the previous example. Pause the video, try this on your own, and then we'll look at it together. Okay? So to compute these things, the probability being less than or equal to 1, well, that's just the 1 over 32. That's this one right here. Okay, the probability being less than or equal to 2 would be that one plus the next one. So this is 2 out of 32. The probability being less than or equal to 3 is the first 3 things added together. So now let's see, if I think of that as being 2 out of 32, this would now be 4 out of 32. And remember, we're eventually looking for the median here, right? I'm nowhere near a half yet. So I'm going to go to the next one now. The probability being less than or equal to 4, I would now add 1/8 to that. So that's 4 out of 32. So if I take this one plus another 4 out of 32, that gets me up to being 8 out of 32. Okay, I'm still not to a half yet. I'm going to now move into this next one here. Okay, I'm now taking this one and adding the quarter here. That's another 8 out of 32. That's 16 over 32. That's a half. Yay. Let's look at the last one because it asked us to find it. The probability being less than or equal to 6 would be me adding that on. Oh, and duh, that makes sense. That should be 1 because at the end of your probability distribution, it should all add up to 1. Now, do you remember what we said in the previous slide about finding the median? The median is supposed to sort of be, the smallest number where you go above a half. Well, we actually hit a half right here, right? A half happened at 5, and then 6 came right after it. So this is sort of like what happens when we're working on the median with a general set of statistics, and the middle number happens to be right in between two things. I find the average of those two things. I add together 5 and 6, and I divide by 2. That gets me 5.5. So the median for this probability distribution is 5.5. Now, I'm hoping that one made sense. If you've got questions about that, make sure that you send me a message about it or an email about it so that I can help to clarify that for you. All right, I've got some good news. We need to talk about mode, which is really like a quick little breather in the middle of this lesson. Hopefully you remember that the mode of a set of data is basically the data point that occurs most frequently. So when you're working with mean, median, mode for general statistics, you just look for the number that happens most often, right? It shouldn't be surprising then to find that the mode of a random variable is just the value of the variable that has the highest probability. If the mode is the thing that happens most often, or the number that shows up most often, then in the probability distribution, it should just be the variable value that has the highest probability. Okay? So, as an example here, I'm going to ask you to find both the median and the mode of this probability distribution. So pause the video, go ahead and try one more median for yourself, and then the mode should be a nice, quick, easy thing that happens right at the end. Okay? So we noted in the previous slide that the best way to find the median is to take a moment to compute all of the cumulative probabilities, right? So the probability of being less than or equal to 10 is 0.2, of being less than or equal to 20 is 0.5, of being less than or equal to 40 is 0.9, and this is 1. And we see right here that our 50% mark happened right in between 20 and 40. So our median of S would be the average of 20 and 40, which is 30. So we found our median, and then the mode of S is really just the thing that has the highest probability. 0.4 was the highest of all the probabilities, so my mode is going to be 40. Finding the mode for these things is really straightforward if you have a complete probability distribution. Now, you may recall from our study of statistics, or from the second slide that we talked about today, that mean, median, and mode are all measures of center, like the center of the data. And we're now going to turn our attention to measures of spread, or how spread out our data is. And so hopefully you remember that one of the terms that we talked about back in statistics was this idea of variance and of standard deviation. Okay. Now for this lesson, I'm really just going to be able to show you formulas for these things. The definition and the derivation of this is something that I don't have time to get into at present, although if it's something that's really interesting to you, it could be something that you look at for your math exploration or for your IA. So we can find the variance of a random variable, and the notation we use for that is VAR of x, the random variable, is found by this formula. Okay, so the E of x that you're seeing here, this E of x is the same expectation that we talked about before. This one here, this E of x squared, is actually is pretty easy. It's understood that E of x squared is really the same computation that we did for finding the expectation, but instead of doing x times the probability of x, you're doing x squared times the probability of x. Okay, we will be looking at an example of this, so we'll be making it a little more clear. But the idea here is you do this expectation of x squared, and then you subtract the original expectation, which has been squared. And this formula is in your formula book, but you can also remember it as the mean of the squares minus the square of the mean. And then just a quick reminder here, remember that standard deviation is always just found by taking the square root of the variance. So if a question asks you for standard deviation, you just find the variance and square root it. If a problem gives you the standard deviation, you can just square it to get the variance. They're very, very similar statistics. So now we're going to look at an example of how we find this idea of a variance. So I'm doing a lot of reuse of probability distributions here. Consider the probability distribution from the previous example. I'd like us to find here the expectation of this random variable, and I'd also like us to find the E of s squared. So I hope that you guys are willing to give those a shot on your own. This one you should easily be able to do on your own. The second one, if you follow the instructions on the previous slide, you should be able to do it. If you're nervous about it, you can watch me start it and then do it on your own. So E of s here, E of s is going to be, remember we just take the value of the random variable times its probability, plus the next value of the random variable times its probability, the next value of the random variable times its probability, and then the last value of the random variable times its probability. Finding the expectation is really straightforward. This is all we need to do for it. Okay, so this means that E of s is, let's see, this is 2 plus 6 plus 16 plus 6. And so if I put all those things together, I'm getting, looks like 30. Yep. So my expected value here is 30. Again, I think it's worthwhile to take a moment and think about the problem. Does that make sense? Well, yeah, I mean, 30's kind of in the middle of the data set. It looks like half the numbers here are below 30, half of them are above 30. Like, I can't tell for sure that this answer is right, but it feels like a reasonable answer in light of everything that I'm seeing here. So now the second part of A asked us to find E of s squared. And I switched to a different color here because I want you to note that this is a different computation. This isn't like, it's not like, the next step. This is a different statistic that I'm computing. So for E of s squared, what I mentioned in the previous slide is you do it just like E of s, but you square the data points, okay? So that 10 becomes 100 times the probability of 10, plus 400 times the probability of 20, plus 1600, that's 40 squared, times the probability of 40. And finally, 3600 times the probability of 60. Okay, so if somebody asks you for E of s squared, you just square your data points. If for some reason somebody asked you for E of s cubed, cool, you'd cube the data points. That's just what this notation does. Okay, so now let's go through and finish out what this computation is. 20% of 100 is 20. 30% of 400 is 120. This one over here is 640. And this last one over here is 360. When I add all these things together, it looks like these things make 1,000, and this makes 140. So I'm looking at 1,140. Great. So now that I've got what this e of s squared is, I'm ready to move on to part B in the problem. Part B asks, hence, find the variance of s and then the standard deviation of s. So the formula that we learned on the previous slide is that we find the variance by doing the mean of the squares minus the square of the mean. Okay, which means that I do this 1,140 minus the 30 squared. That's 1,140 minus 900. So I'm getting the variance to be 240. And then the standard deviation of my variable is really just the square root of 240. And that could probably be simplified, but IB's not going to take points off if you leave it in that form. I guess the one more thing I will say about this, the square root of 240 is somewhere in the range of 15 to 16, and it's worth thinking about that because, again, we want our standard deviation to make sense. Standard deviation is supposed to sort of be this idea of a measure of average distance away from the mean. So if my mean up here, 30, was somewhere in the middle here, this idea that data is on average about 15 away from 30, like that makes sense. 15 keeps us within the range of data that we had here. If I got that my standard deviation was like 80, it means that my data is on average 80 away from the mean. That doesn't even keep me within the range of data that I have. So that's a way that you can kind of check for reasonability on this. I know that we're far into this video and you may be running out of steam, but stay with me. I've got one more example to look at, and I don't think that it's a super complicated one, but it's something that I want to explain to you that happens. It's really important to pay attention to the random variables in problems. Sometimes a problem will introduce multiple random variables. And in the next problem, we're going to see a game where you might like win a different prize depending on a roll of a die. And so there's this idea that there might be one random variable for the roll of the die, and then another one for the prize. And there's a question of like, which of those things do I care more about? Do I care more about what number comes up on the die, or do I care about like how much I win? And so you want to make sure that you're thinking about that when you're answering questions. So here we go. I want us to consider a game where a player pays $3 to roll a biased four-sided die and then wins a different amount depending on the result of the die. The table below shows the probability of each result as well as the amount that the player wins for that result. Okay, so you know, in the middle here, it's almost like you've got the probability of something happening. Up at the top, maybe you have the random variable d representing the die result. And down on the bottom, maybe we have the random variable w that represents the amount that the player wins. Okay, so for part A, I want you to think for a minute, and I really, really want everybody to think about this for a moment. Explain why a player's net return for rolling a score of 1 is -1. I know it says that they win $2, but why does that mean that their net return is -1? And hopefully it's clear to you, well, they had to pay $3 to play the game. So it's like they paid $3, and then they're like, yay, congratulations, you won $2, here's $2. That means that their net return for that game was -1. They basically lost $1. So that's how I would express that, right? Because they had to pay $3 to play, but they only won $2, their net return for the game was -$1. Now part B asks us to compute the player's expected, and this is really important, it's their expected return, not the expected die result, not the expected amount that they win, but their expected return. Right, so it's almost like I need another random variable here, right? It's almost like I want to do e of r, and I might want to write down, like, what is the return, and I'm sorry this is all squished in here, what's the return for each of the times they play the game? Right, so pause the video, write down, like we know this return is -1, write down what the return is for each of these things, and then use that to compute their expected return. Well, their expected return here is 0, because they're going to pay $3 and win $3. Their expected return here is 2, and over here their expected return is 7. Okay, so their expected return here would be -1 times the probability of that happening. There's a 70% chance that they're going to lose $1, plus 0 times 0.2. I guess I didn't really need to write that one because its effect is going to be 0, but I wanted to write it. We've got 2 times the 8% chance that happens, and then finally $7 times the 2% chance that that's going to happen. And then when we run through and compute these things, E of R means, so this is going to be negative 0.7 plus 0 plus 0.16 plus 0.14. So if I add these things together, this ends up making for 0.3. So E of R is going to be negative 0.4. So that's my answer for part B. And then finally, part C, the very last part here, part C. Explain what the answer to part B means. So I'd like you to pause the video for a second and think about what this means and try and put that into a sentence. And if you're looking for sort of like extra credit here, you might think about, there's two different ways to interpret this based on the perspective that you have in the problem. I'll say that, and then we'll talk about what the answer is going to be. So what this effectively means is, it means that the player's expected return is negative 0.4, like losing 40 cents. So it's like every time they play this game, on average, they are losing 40 cents. So what's the other perspective that I was talking about? Well, the other perspective is there's someone that's running this game. What does this answer mean in their context? Right? Well, it means every time they can get somebody to play this game, they're earning 40 cents. So if you were like setting up a game at a carnival or something, and you were running the thing, you wanted to figure out sort of how much money you were going to make over time, the question is, can you lure enough people in with the hope of winning $10? And you're okay paying at $10 every once in a while because you know that on average, as the game organizer, you're winning 40 cents. So that's another way to think about this. So I know that was a lot to take in this lesson, but I hope all of that made sense. As always, if you've got questions or if there are things you're confused about, please, stop in and see me at one of our classes or send me a message so that I can help. But best of luck as you work through all of this.